So very quickly, again, we look at the example, the case where the frequency of excitation is equal to the frequency of the system, the natural frequency of the system. This is the form of the particular solution. This is the derivative. So again, as we were saying, we need to go through the exact same steps that we saw before. So we need to look at the first derivative, second derivative. We can plug the second derivative and the function in our equation of motion. We can simplify significantly because we are under the assumption that omega is equal to omega n, which means that these two terms are the same. One is positive, one is negative. We can get rid of them. We can further simplify because here we have cosine of omega t on both sides, and then we can find our amplitude based on the amplitude basically of the external force and its frequency. Once we find the amplitude, we can plug back here, and this is the particular solution. Once we have the particular solution, we know that the total solution is given by the summation of the homogeneous solution and the particular solution. The homogeneous solution has the exact same form that we saw before when we didn't have any external force, so we can write the entire solution. We still have A1 and A2 that need to be determined. How do we determine them? We can use the initial conditions, which means we can use the condition for position, initial position equal to x0. We can use the condition for velocity, initial velocity equal to v0. Of course, if we want to use the condition for the initial velocity, we need to use the first derivative of the solution. And then with these two equations, initial position and initial velocity, we can find our two constants, A2 and A1. When we use these two constants, we plug them in our total solution, we can finally plot the response, and we can see that in this case, the plot looks like this. Which means that, very, very important, if the frequency of excitation is equal to the natural frequency of the system, the amplitude of oscillation, the amplitude of displacement, actually increases in time. So this is in structural analysis, this is a very, very dangerous condition. We always want to stay very far away from the natural frequency when we apply a certain external dynamic force, because theoretically, from a mathematical point of view, this amplitude will grow to infinite, but in structural analysis we know that if we have a certain displacement, if the displacement is too big, it means that we have too much strain, it means that we will have plastic deformation and then eventual failure of the entire structure. So we don't want that. We always want to stay away from the natural frequency of the structure. Makes sense? So we talked a little bit about also what happened when we look at how the amplitude changes with the frequency of excitation. And actually today we will look at this even more in detail. So we said that if we want to plot the amplitude as a function of the frequency of the external force, we will see something that look like this. Again, when the value of the forcing frequency is equal to the natural frequency, theoretically the amplitude goes to infinite. Again, of course, this is valid for a situation where we have no damping. Then we looked at a problem that involves an external force that changes in time. We know the amplitude and frequency of the force. We are on an inclined plane. We also know the characteristics of the system, so the K of the spring, the mass of the body, and we want to determine the equation of motion and and the of the system. We started from the free body diagram. From the free body diagram, we can write the equation of motion. So we look at all the forces involved equal to mass times acceleration. In this case, we have an inclined plane, which means that there will be a certain component of the gravity that will have an influence on what's going on the body, which means that there is some static deflection. We can take that into account when we look at the static equilibrium. So from the static equilibrium, we have that the component of the force, of the gravitational force along the direction of motion must balance the force that comes from the spring, again when we have that static deflection. And then when we apply this one, we get rid of basically this term here and this term here. So we have our equation of motion in standard form. We can always divide by the mass, so we have x double dot plus omega n square x equal to f0 sine of omega t, and then we have to solve this one. This equation is very, very similar to the one that we saw before, for which we went through all the steps, calculating the first and second derivative, plugging the function and derivative, and then finding the particular solution, finding the total solution. So we could use what we did before, but actually we can't, because in the previous case the external force was f0 cosine of omega t. In this case we have f0 sine of omega t. Again, of course we go through the exact same steps, but the derivatives will look a little bit different. So that's why the final solution will be different. Here we have a summary of all the steps that we need to go through, and then eventually our response should look like this. X of t is equal to negative 0.0732 sine of 4.472t plus another term 0.1309 sine of 2.5t. I hope you spent a little bit of time to go through these actual steps, and I also hope you found this exact solution. Yeah. So here we had that yeah. Yeah, we have to follow the exact same steps. Now, if we compare like the symbolic solution with the final solution, we will have that we have only the term in sine, which means this a1 would be this one. We don't have the term in cosine, which means that a2 would be 0. And then we have this term here. So this f0 divided by omega n squared minus omega squared would be this term here. So basically these are the quantities that we need to find. Right, if there are no questions, we can move to the next step. So as you can imagine, as we did for free systems, we went through several cases. So we went from the free undamped system to the free damped systems. In this case, we are going to do the same. So far we looked at forced undamped systems. So now the next step is to look at forced damped systems. So you should have at least an idea of how our equation would change, but we can look at this together. So let's assume that we have a system that again is forced damped, forced and damped. Again, forced means that we have an external force, and damped means that we have some damping effect. We can create our schematic. So if this is our mass that moves in the horizontal direction only, in this case, we still have a certain spring with an elastic constant k, And then we also need to have, in this case, a certain dashpot, which is the damping element. This is what makes the system damped, but we also have to make it forced, which means that we have to apply the external force. Of course, it must be a time-dependent force, so we can call this f of t equal to f0 cosine of omega t. Okay, now we can go a little bit faster on this phase because we already know what we need to do. We need to use the free body diagram. From the free body diagram, we would have three forces. One is the external force, one is the force of the spring, one is the force of the dashpot. The external force is time dependent following this equation here. The force of the spring depends on the displacement that is occurring around the equilibrium position. The force of the dashpot depends on the velocity of the body. So by looking at all these three forces, we will obtain an equation of motion that looks like this: mx double dot plus cx dot plus kx equal to f0 cosine omega t. So basically this is the same equation that we had last time, but we add the contribution of the dashpot where we have cx dot. Even in this case, we want to write the equation in standard form, which means that we normalize with respect to the mass. When we normalize with respect to the mass and we also introduce the damping ratio, the zeta parameter, this equation becomes like this. We have x double dot plus 2 zeta omega n x dot plus omega n squared x equal to, we use the lowercase f, so in this case we can do the same, lowercase f0 cosine of omega t. Makes sense? Okay, now, exactly like we did before, we have to look at the solution of this non-homogeneous equation. Non-homogeneous because we have the term here. So if it is a non-homogeneous equation, the solution x of t will be equal to the summation of two contributions. One is the solution of the homogeneous, and the other one is the solution of the particular equation, or the particular solution. So as we did before, we can start from the particular solution. So now this is what is slightly different, and what will make our equations, our functions, a little bit more complex, I would say, because for an equation like this, the particular solution can be of the following form. We have xp equal to a, we can call like as, just to use a certain subscript, cosine of omega t plus bs sine of omega t. So in the previous case, we had only actually one term. In this case, again, by trial and error, we have that the solution of an equation that looks like, the particular solution would look like this. So now that we have this general form of the particular solution, what should we do? What do we need, and what should we do to obtain what we need? We can start by taking the derivative. Why do we need to take the derivative? Okay, so that we have another expression. The goal is to find these two constants here, AS and BS. How do we find these two constants? We need to take the first derivative, the second derivative, and then we can plug here the first derivative, here the second derivative, here the function, and then we can see what we obtain in terms of equation. So for the first derivative, we have a derivative of this term here, which is negative omega as sine of omega t plus bs cosine of omega t. Then we have the second derivative, which means we need to derive this one more time. So we have negative omega square as cosine of omega t minus omega square bs sine of omega t. So now that we have this expression for the function, the first derivative and the second derivative, we can simply plug them here, here, and here. I'm not gonna write, this is just copy and paste, but I will write the next step, because once we plug this, I missed an omega. Where did I miss an omega? Cosine of omega t times omega, right? I always miss some omega somewhere, and Edwin always catch it. Thank you very much. Okay. So now that we have, again, the function, the derivative, and the second derivative, again, we can plug them here and here and here. Again, it's going to be just copy and paste. I want to go to the next step, because actually after we, again, plug these three in the equation of motion, we can actually rewrite in a slightly different form that will be very useful to find our two constants. So after, again, one step, I'm skipping one, we can rewrite as follows: cosine of omega t times negative omega square as plus 2 zeta omega n omega bs plus omega n square as minus f0 plus so there are two terms. This is the first one, and then the second one will be sine of omega t minus omega square bs minus 2 zeta omega n omega as plus omega n squared bs equal to 0. Yes, so these dots here are to show or to hide actually that we are plugging basically these three expression here in the equation of motion. So if you take this, you should plug it here, then you take this one and you should plug it here, and then you take this one and you should plug it here. Once you do this one, you will obtain this term plus 2 zeta omega n times this term plus omega n squared times this term equal to f0 cosine of omega t. Now if you take this and you rearrange all the terms by putting together all the cosines and all the sines, this is what you obtain. So now we have to recall a little bit of trigonometry from this, because in order to solve this expression here, in order to find again AS and BS, we can look at the fact that here we have one term that is cosine of omega t. Here we have one term that is sine of omega t. They have the same argument, so it means they cannot be 0 at the same time. Remember that here we have the first term plus the first term equal to 0. So in order to have this term plus this term equal to 0, they need to be equal either both 0 or one opposite to each other. So what we can consider is that, again, since this and this cannot be 0 at the same time, the only way in order to have 0 for this whole expression is to have at the same time this equal to 0 and this one equal to 0. So basically from this equation we come up with actually two equations. The first one is this term here equal to 0, and the second is this term here equal to 0 as well. So we have negative omega square as plus 2 zeta omega n omega bs plus omega n square as minus f0 equal to 0. And then the second equation would be negative omega square bs minus 2 zeta omega n omega as plus omega n square bs equal to 0. So basically from one equation, from one trigonometric equation, because we have cosine and sine, we ended up with two algebraic equations. And since we have to find two constants, as and bs, two equations is actually what we need. Now also we have a little bit of algebra. We can actually rewrite this in a matrix form, because here we have as, bs, as, here also we have bs, as, bs. We can group together what we have here in as, we can group together what we have here in bs. We can bring this on the other side. Again, we could rewrite this one in a matrix form, in a 2 by 2 matrix form. So once we go through, or we can simply do a substitution from one to the other one to find the two constants. So again, even in this case, I will skip these steps because this is not what we are looking for. So when we solve this system of two equations, we find finally as to be of the following form. Omega n square minus omega square, that multiplies f0, and then at the denominator we have omega n square minus omega square, this is also squared, plus 2 zeta omega n omega squared. For the other constant, which is bs, we have 2 zeta omega n omega f0, and then in the denominator we have omega n squared minus squared plus 2 zeta omega n omega squared. So now that we have these two, as and bs, we can plug them where we were before. So here in xp, so here we have as, here we have bs, so we have actually an expression for xp. We can look at the expression of the homogeneous, the solution of the homogeneous equation, plug it here, and then we should go over again the same thing that we did before, so the derivatives, so that we can find the constants. Again, in this case, a lot of algebraic steps. I'm not going to show you all of them, But I want to show you actually the final solution that we find as a function of the initial conditions. So the textbook has the expression, and in the textbook it has 4 lines. This is how it looks like. So trust me, you don't want me go through all these steps to obtain this expression here. All right, so this is the form of the solution that we have when a system is damped and forced and subjected to an external force that looks like the one that we saw before, which means F0 cosine of omega t. This form here. So actually, I think now we can comment a little bit this this expression here, because we can notice one first thing is that this solution here is given by the summation of 2 contributions. One contribution is this exponential term multiplied by whatever is within this curly bracket. And then we have the other contribution, which is this term here. Also, of course, when we look at this equation here, this function here, we can see that we have the initial conditions. Here we have the initial velocity, and here we have the initial position. So it changes when we change the initial conditions. And it also depends on the external force, because here we have this term F0, which is the amplitude divided by the mass of the external force. We also have omega here, this term omega, which is the frequency of oscillation of the external force. So when we change the external force, of course, the response changes. And then we also have the term here omega n. So it means that if we change the parameters of the system, our response will change. And we also have this term zeta. Zeta, remember, is the damping ratio. It depends on the damping coefficient of the dashpot that we have. So of course, by changing all these parameters from the external force and from the system itself, the response will change. Again, the other factor that we just mentioned is that we can see that there are two contributions to the total solution, and now actually we can rewrite this expression here in a different way, a little bit more simple way, which is also more useful for looking at it by a physical point of view rather than just a mathematical point of view. So that expression I'm going to write so we can write also the response, the solution, as x of t equal to a certain constant a multiplied by an exponential function, so e to the power of negative zeta omega n t times sine of omega d, this is the damped frequency, t plus phi, and then we have to add another contribution, which we can call big X times cosine of omega t minus theta. Now, if we look at the equation, we can write the expression also of all these constants. We can write the expression of A as a function of the initial conditions and the characteristic of the system. Same thing for phi, big X, and theta. These are all parameters that depend on what kind of external force we have and what kind of system we have. But the most important thing at this point is that when we look at these two contributions, the one on top corresponds to the transient of the solution. The one on the bottom corresponds to the steady state of the solution. So let me write down this is the transient. Is a transient response, and this one is the steady state response. Because the steady state response changes in time. Now, what do we mean by steady state? Steady state, we mean that the amplitude doesn't change of the... I was going to actually draw something to make this a little bit more clear. So just give me a couple of seconds so I can explain first these two, and then we can look at a graph that can explain a little better. So I was saying that, again, the first portion is the transient, the second portion is the steady state. What does it mean? It means that if we look at the change of amplitude in time, there will be the first portion of our graph starting from the initial time, from t0, that will be mostly influenced by this portion of the response. And then there will be, so after this transient, there will be one portion of the response that will be influenced mostly by this part of the function. So this is a function of time, because if we look at a certain plot, for example, so x as a function of t, what I could expect for something that looks like this. For example, again, this is just qualitative. So for example, we can have something that looks like this. For example, we have an increase, and then after a certain amount of time, again, we reach the steady state, which means that the amplitude eventually remains the same. So this is what we mean by steady state. So steady state doesn't mean that the system doesn't move anymore. It doesn't mean that it's static. It means that the amplitude of oscillation remains constant in time. This is what we mean by steady state. So that's why here we have, for example, in this case, let's say the first portion up to here, this will be the transient, where there is a change in amplitude, and this would be the steady state,